Hey Geometry, so today we're going to put all of our logic together and actually formally do some proofs. We've actually done some of this before, so this and some of our other lead-up chapters to this, but we're going to finally dive in full. So with algebraic proofs, we've got a bunch of different properties. Mostly we're talking about these are properties of equality, but they can apply to congruence in a lot of cases as well. So as long as A, B, and C are real numbers, our addition property looks like this. Basically, if A equals B, so we're going to start out with a bunch of, these are conditional statements, and then we're going to string together a bunch of conditional statements using the law of syllogism to make our proofs in most cases. And so if A equals B, then A plus C equals B plus C. So if you have two sides of the equation equal to each other, we can add C to both sides. And similarly, if A is equal to B, then A minus C is equal to B minus C. So we can subtract some constant C from both sides, some real number. Multiplication property. So if A equals B, again, a bunch of these are going to start out this way, then A times C equals B times C. And the division property, if A equals B, then A divided by C equals B divided by C. You can divide both sides. All right, so we have the substitution property next. So if we have if A equals B, oh yeah, sorry. I'm looking at my previous note here. I forgot to mention up here, and C is not, so as long as, I got this on the wrong side. So if A is equal to B up here, and I'm going to throw this in here, and C is not equal to 0. Can't divide by 0, of course. So that's what I was looking there in my note. Then, so over down here, if A is equal to B, then A may be substituted. So replaced for B in any expression. So yeah, we can replace any B with an A and vice versa as well. All right, so our distributive property sets up like this: A times B plus C. So if we have two things being added inside parentheses and then multiplied by A, we can distribute that A. So it's A times B plus A times C. Kind of one interesting thing about this distributive property, this is actually kind of our combining like terms if you think about it kind of in reverse. If I have, and if we kind of reverse this around, so BA plus CA, if I change the order of that multiplication, same thing, BA times CA is equal to B plus C times A. That's actually the combining like terms, right? So this is combining like terms. So you can call it combining like terms. You can also call it an application of the distributive property if you want. Combining like terms. All right, the reflexive property is a weird one, but we'll throw it out there every once in a while if we just need to make a statement of something equals itself. The reflexive property. And then the symmetric property, if A equals B, then B equals A. We can flip that around. And then finally the transitive property, if A equals B and B equals C, then A equals C. And so it's kind of substitution as well. I'm okay with either of those. With the transitive property, we're substituting in C for B or A for B there. It works either way. So note that segment measures and angle measures are all real numbers, so properties of real numbers can be used to discuss their relationships. And then we're dealing with real numbers here, so addition properties, subtract, all those properties can apply if they're in equation, and a lot of times some of this stuff is in congruence as well. All right, so for an example, if we were going to go through here with some justification, this are kind of our two-column proof. We have our original equation. So here we have, they've kind of we can see what's the justification for the step they just did. You can call this distributive property. So the distributive property, and then the next step here, we're combining like terms. Sorry, and this is, or you could have also said distributive property. Right, it's kind of an application of the distributive property. And then here, so we've combined like terms to get from this step to this step. But you could either think of it as adding 18 to both sides or subtracting negative 18. Honestly, addition and subtraction properties are kind of the same deal, just whether you're dealing with addition of negative numbers or subtracting negative numbers, it's, you know, it just turns into the other. I'll call this addition property, but you could also call it a subtraction if you really want to, subtracting negative 18. Addition property. And then finally the division. You can also think of it as multiplying by negative 1/10, but I'm going to think of it as dividing by negative 10. So whatever way you want to go with that to justify that one. All right, so moving on to, so this is kind of more into some proof. Proof is a formal logical argument that shows a statement is true. Two-column proofs of statements and the reasons that show the logical order of the argument. The statements on the left column, so the statements are the left column and are the results of applying definitions, postulates, and theorems to statements already made. The reasons in the right column are the justification for each statement. So, you know, we have kind of we'll have each of these where we're kind of doing syllogism. If this, then we can say that. If this, then we can say that. If this, then we can say that. And kind of it takes us back and forth until we can, use all of our good deductive reasoning to get that proof together. So our original statement here, our original reason, is always just going to be kind of what we're given. We're told some statement is true. So if this, that's their given statement. So if this is true, prove that. All right. So that's our given. And then we start looking at all of our algebraic steps here. So here we have distributive property again. Distributive. And then we want to get rid of this 5, so we could add 5 to both sides. You could also think of subtracting negative 5, whatever way you want to do it. Well, I'll call this addition property. And then division property. To go from the 3x plus equals 6 divided by 3 on both sides, and that leads us to x equals 2. And that gets us to where we end up there. All right, so that's algebraic proof. This next one is actually, there's maybe some algebra in it, but there's also some geometric segment stuff in there as well, which really leads into kind of our next couple of sections. So first of all, here we're given that MA is equal to TH, so the distance from MA, this distance here, is equal to TH. So we have those two distances are the same, and that's given. All right, and then after that, we have AT is congruent to AT. So that is the reflexive property. There it is being used. The reflexive property, AT is congruent to its, or not, the segment's congruent to itself. They're saying that the distance is equal to itself. So then MA plus AT equals AT plus TH. So if we look at this first step, we're adding AT to both sides. So we are doing the addition property. We're adding the same thing to both sides. If MA is equal to TH, then we can add to AT to both sides and it'll still be equal. Addition property for that one. All right, the next one, this is where we get a little off algebra here. The left side they turned into MT. So they said MA plus AT is MT, and that is actually the segment addition postulate. So we're getting a little outside algebra at that point. Addition postulate. Sorry, postulate, postulate, I'll abbreviate there. And then similarly, AH is equal to AT plus TH. That's another segment addition postulate. And then finally, we can actually get MT is equal to AH if we do some substitution. So this right here is the same as that. We're actually, if MT is equal to MA plus AT we can think of as just one kind of entity, one value. We can replace that with MT on the left side, and then AT plus TH is right there, so we can replace that right side with AH. So this is really just a kind of a double substitution for that next step.